Welcome, everyone. We'll get you to put all your headsets on. I'll wait a minute till I see a whole bunch of glowing colors. Excellent. I am your host, Aaron Peterson. I'm a solution architect here at AWS, and I'm here on stage 6 for the next 2 days. We have a really exciting topic, but first, a little bit of housekeeping. If anyone's got mobile phones, if you could put them on silent, probably won't distract you, but might distract the presenters who don't have headsets on. We have the app. We'd love, at the end of the session, before you head off to your next thing, if you could fill out the survey. The button appears towards the end of the session, so if you go in there too early, you might not see it, but it will be there towards the later few minutes of the session. I'm really excited about this one. I think this one has a really catchy title, and the room is full, which is great to see. The last time I heard anything about identity swapping, it was probably with a movie called Face Off with Nicolas Cage and John Travolta. Well, it's not about Hollywood anymore. We're going to talk about it with technology. So I'd like to present to the stage and welcome Nagib, Matt, and Luke. Please, come on up, guys. Thank you.
Hello and welcome to building Netflix's It's What's Inside a Game journey. Hopefully we'll give you a detailed look into how we have ideated and then went about building this innovative journey in AWS, where up to 6 players can simultaneously swap their identities in the digital world. Imagine you swapping with your friends or your friend looking like you, that kind of an experience. So very innovative, very unique. That's been built by the wonderful team from AKQA. But let's start with the bit of introductions first. So my name is Nagib Shah. I'm a solutions architect at AWS. And I'll be your host for this particular session. And I have with me Luke Ballantine, technology director from AKQA, and Matt Byrne, who is the platform engineering lead. Luke is going to be walking us through how we went about creating this idea itself, how we set up this experiment, and how it sort of led to some of those technological decisions that we needed to make. And Matt is going to help us go under the hood effectively, taking a deeper look inside, especially around some of those compute challenges that we actually had or faced for this particular problem. So, but first, Matt, I want to ask you, help the audience understand exactly what is this movie about and walk us through the idea that we had and the result.
Sure. Thanks, Nagib. So this was the movie that Netflix launched in October last year for the Halloween season. So it's what's inside the movie. And it's a movie about body swapping. So if you're as old as me, you might remember a few of the old sort of body swapping movies like Freaky Friday or Like Father, Like Son or Face Off. But this is a fresh Black Mirror-esque take on the idea of body swapping, where a group of college students get together for a reunion. They haven't seen each other for a few years, and someone brings this futuristic tech inside the suitcase and allows them to do sort of body swapping in mass. So what we built for Netflix is, go back one, yeah, thank you. So what we built for Netflix was a true world first. It's a video conferencing game that allows you to puppet realistic AI clones of your friends in real time. And when we get into details of some of the hardware, you'll understand why it hadn't been done before. So I'm going to sort of fast forward to the end and just show you what we built. This is one of the in-game assets that we showed to users. It's a really good explanation of how the gameplay works, and it's kind of important for context, especially when we get into sort of Matt's session about the technical details of this.
Prepare yourself for an unforgettable experience that will take you out of your mind. As our revolutionary one-of-a-kind machine is being synced with your consciousness, please pay attention to the following instructions. When the game starts, you will randomly swap bodies with one of your friends. From that point, everyone will see and hear you as that person. Likewise, your friends will experience the same thing. For the best body swap experience, keep your camera stable and avoid body movements. Keep arms, legs, and anything else out of frame. No hats or sunglasses either. The objective of the game is twofold. Objective 1, fool your friends. Don't let them know who you really are. Objective 2, guess who is in whose body. At the start of each round, a question will appear on the screen. Players will take turns responding to this question. Only one player can speak at a time. When it's your turn to answer the question, you'll have 20 seconds, so use your time wisely. Once you've finished speaking, you can end your turn early. When you think you know who is who, simply drag the Polaroid of the real player to their box. You can change your guesses as often as you like, but your guesses will be locked once the game timer expires. When 10 minutes are up, the game is over and the truth will be revealed.
Thank you, Luke. That's indeed very unique, and I can't believe what we've accomplished in effectively such a short time frame for this particular project. But I want to rewind a little bit and go back to this ideation phase, where, on a pen and paper, just talking about the concept to how you went about defining the actual final solution. So can you walk us through some of that a little bit?
Sure, yep. So,
my bad, yeah. So, my bad. I think let's start, before I wanted to set the scene and context, number one, there's a couple of principles that really worked well for us in this case, and there was one particular one that is really near and dear to me. That is think big and start small and scale fast. Now, what this means is effectively making reversible decisions, and which allows faster experimentation. And lastly, with any team, there's always going to be disagreements on how we approach a particular problem, but it's important to disagree and commit at the end of the day, which allows you to move forward. And the second principle that I want to sort of mention over here is getting to know or the know. And what this effectively is for a successful solution, you need to sit at the intersection of customer desirability, business viability, and technical feasibility at the end of the day. Now, if you can strike the right balance across the three, that's when projects tend to be really successful. And I kind of sort of wanted to mention it because they resonate really well with some of the approaches that you took. So if I can now ask you to sort of go into some of that.
Sure. So we first got wind from our Sao Paulo studio, actually, that who do a bit of work for Netflix, that they were looking for like a really innovative technology activation to support the release of their new movie. And so we canvassed the studios in New Zealand and Australia for some ideas, and we went and presented a couple back to Netflix, and this is the one that they actually picked. So the idea was a body swap call. On an innovative website, people will join their friends on a video call, swap bodies, and imitate each other. Then in a cutting-edge game of deception, players will vote on who is who. And we deliberately kept this idea quite vague because we weren't sure how we were going to build it. But they immediately loved it, and they said, this is a digital version of the body swap experience, what the characters in the movie actually experience. So yeah, they asked us to get started straight away. So they said, how would this work? This was 8 weeks out from the release of the movie. And so we said, well, we'll run a 2-week proof of concept. And in that 2 weeks, we're going to explore the current state of the art. We will come up with some game designs, and we'll have a technology demo for you about how it's going to work, and a budget. And this was 8 weeks out from the release date. So they said, great, get started. So one of the things we really wanted to look into in a bit of detail was whether we could do this in real time. I initially didn't think it was going to be possible, and our kind of fallback approach was effectively maybe like a recorded message. You record a message and then you use AI to transform the message, and then you watch it back together as a group. But we really wanted to do our due diligence on real time and see if it would actually be possible. So we knew these were our 3 big rocks that we had to overcome that we didn't really know how to get past at this stage. So the first one was video cloning, then voice cloning, and then we have to work out how to bring them together in a video conferencing experience.
Awesome.
So this was the first big rock, video cloning. So we did look at some some other technologies like sort of face swapping, but it didn't really suit our use case very well. So we eventually landed on live portrait, which is like a face swapping portrait animation type experience. So what it allows you to do is capture a single frame from a photograph or a webcam, and then with a driver video, you can puppet an AI clone of someone, and it looks very realistic. But what we found was that to run this at 24 frames per second, it required some massive compute power. So we needed a NVIDIA 4090 GPU, so it's the absolute latest, most expensive sort of consumer-grade graphics card you could get at the time. And it ran fine on that hardware. The next challenge was voice cloning. So, we looked at some sort of text-to-speech options, but obviously they weren't really going to suit our use case. So, and we eventually landed on retrieval-based voice conversion. It's a relatively new technology that allows you to do speech-to-speech translation. So it gives you real-time, low-latency speech-to-speech, and it preserves the speaker's emotional tone and their vocal attributes, which is sort of very important if you're sort of playing a guessing game. We want some of the original characteristics to carry through. Again, it was really a challenging thing to run. It required massive compute power.
Yep, so I kind of wanted to highlight a couple of things over here, obviously, is the fact that the 24 frames per second was the must-have in order to make it a very smooth experience in the digital end. And the second one was, coming back to that getting to know and know, we actually now know what kind of infrastructure we need for this, which is effectively P4D 24 XLs at a minimum in order to sort of make this happen. And obviously with the audio, throwing enough compute at it in order to make this a very smooth, as realistic, near real time as possible. So, which brings obviously the last big rock, which is the video conferencing. And Matt, I remember having several conversations with you, one of which was also, hey, how about we just build this from scratch, from the ground up, using some of our services. But walk us through some of the thought and ideas that you sort of considered.
Yeah, I think as devs we have a tendency to try and reinvent the wheel sometimes, but the time frame we had for this project and the features we had to implement, a number of which we didn't even know if they were possible, meant it just wasn't really going to work here. So we were lucky to find this open source product called LiveKit, and they also run a SaaS platform which we ended up using. And what it allowed us to do was fully customize the front end of our video chat experience, and crucially it let us split the audio and video streams and then run inferencing on those streams independently and then reassign them back in whatever order we wanted to.
Awesome. So obviously with the previous assumption that we made was, hey, let's do a pre-recorded one. We've effectively invalidated that at this particular stage. The answer is yes, we can do this in real time, and most importantly, we are armed with certain information, P4D 24 XLs, and is pretty much what we need. Provided we can provide enough instances, we can make this happen. So look, I actually want to ask you, with this new information, which we validated through the experiments, what was the final pitch that you made to Netflix?
Yeah, so we went back to Netflix and we ran them through what the game setup would look like. So you jump on your computer, you create a room and share a link with your friends, and then through the gameplay experience, how it'll work is, advance to the next one. Cheers. So you'll swap bodies with your friends, you'll play a fast-paced game of Q&A that'll last about 10 or 15 minutes, and their response was, seriously, AKQA, you're going to do this in 6 weeks? This was 6 weeks away now from the launch date. You're going to do this in real time. And we said, well, we think it's much more impressive to do this in real time. They were expecting us to do a recorded message option. And we said, look, it's never been done before. This will get, it'll get some significant press attention, potentially. This is much more in line with what you're sort of trying to do, we think. But it's going to require some fairly major compute power. So the thing is, people aren't going to be able to run this on their desktops. It's going to require some compute rental in the cloud, but we had a partner for that in AWS.
Awesome, so which brings to the exciting part, and also some of the more tougher parts of this, which is scaling the actual underlying infrastructure. And we're going to walk through some of those components that made this happen, but before that, I kind of wanted to touch on this challenge that we all know about. Number one is, there is a real challenge around GPUs. across every industry verticals. It's difficult to get access to them, whether you want to run experiments, whether you want to run things at scale. For this particular instance, this was a B2C customer-facing use case. We needed a lot of them, and quite reliably so, we needed them. So we had to overcome this challenge. So if you were to sort of deploy GPUs in AWS, there are several options. So obviously there is on-demand capacity requests, there is spot instances, and there's a new one, capacity blocks for ML, that we will touch on. But the on-demand capacity blocks and ML and the spot instances are not really a good option in this particular case. Number one is they're on all the time for the first one, and for spot instances, I think some of us may already know, but they could be interrupted, right? Because it's spare capacity that's pulled forward. So it's not a good fit for a customer-facing use case, which left us the third option, which is effectively allows us to request a desired quantity of instances at a desired time. And I'm going to go through in some of those options in a little bit. But let's talk about, with the capacity blocks, what infrastructure options are available. Now, there is different ML GPU infrastructure that you can request, all the way from P4 and P4DE and P5, which are obviously on the A100 and H100 chips. There's also G4 and G5, which is also available, and our own custom silicon in the form of Trainium and Inferentia. So you have options of picking these instance types for your particular workload. From there onwards, what you would need to do is effectively provide a date window, the total number of instances, and the duration for which you need these instances for. And this is the critical part. We knew the campaign was going to run, movie launch coming, allowed us to plan. How this would work, obviously, is over the other option. If you were to have on-demand capacity requests, there's a lot of wasted capacity in this particular case, because you don't need those instances constantly on. So it's pretty much just sitting there, not really doing anything, and it's not really a particularly greener option. Whereas with capacity blocks, it actually allows you to focus on the time slots that you need it on, and thereby reduce a lot of waste. And that also allows us to sort of do this at a much cheaper clip, which is very important, especially for a solution that we know that it's going to require a great number of GPUs. We need to do it, make it quite cost effective. And this is the bit where, if we were to sort of do this on, let's say, a P5 instance type, and if you do a planning where we do on-demand capacity requests, you can see how, just by the virtue of ML capacity blocks on a 2-week usage, how we're able to achieve up to 42% of savings for your particular use case. So this is extremely cost effective. So we've actually solved a problem for, hey, we need GPU infrastructure, quite a lot of them really fast. How do we make it happen? So with this, obviously, some problems are solved, but there are still key challenges that are left over. Number one being only 6 weeks, 500 concurrent users, which was what the target was, and also efficient use of ML capacity blocks. Lots of GPUs, we needed to make good use out of it. So we've got the underlying architecture right now that would make it happen. And this is where, Matt, I'm going to ask you to sort of step in and help us provide a very sort of detailed view across some of those components. But first, we obviously have a game front end, which allows the end user to come in and invite your friends. There's also a room service, which is built on microservices architectures, and Matt's going to sort of cover a few of them. There's a user upload service. What you alluded to before, we needed to take recording and upload that audio in order for the training to occur. And there's also resource manager, one of the key components in this architecture, because it needs to make sure that there's efficient allocation and deallocation of the expensive GPU resources. There's obviously a lobby service, and there's the core infrastructure sitting in EKS, which is running those 84 P4D 24XLs that we ultimately needed for this architecture. Now, Matt, we can already see there's a serverless and also EKS component to it. Help us walk through some of the components and also why EKS.
Yeah, so for EKS, there's two kind of main reasons. We already had a wealth of Kubernetes knowledge in team from more enterprisey projects, to be fair, but still very relevant. And also it just gave us direct access to those A100s. So we still wanted to use serverless for most of the microservices because it gave us just that delivery speed. But we knew the GPU workload would be in containers, and we knew that the best way to get those containers access to the A100s would be via the P4s, via EKS. So if we kind of have a look at our architecture here, users first hit our app through a React single-page app that's running in S3 and delivered through CloudFront. And their browsers immediately make a WebSocket connection with our lobby service, which keeps track of them in the game and keeps their connection to the game handled. From here, they can either create a new game or they can join a game from an invite that they were sent by a friend. Our lobby service sends messages to our room service, which keeps track of our rooms, so up to 6 people in a room. And that state is stored in DynamoDB. So the first thing that the user comes across is a script, which they're asked to read for about 2 minutes. And that sample of their voice is what we're going to use to train our voice model. So that's uploaded to S3 via API gateway and Lambda functions, validation Lambda functions. And then we do the same thing for a picture of their face, except we also go via AWS recognition for that, so that we can make sure it is actually a picture of their face and not another part of their body. The third key service that you alluded to before is obviously our resource manager. And our resource manager orchestrates our GPU workloads. So once our voice upload is done, an S3 event trigger triggers our resource manager to allocate a GPU, and that GPU is allocated against a DynamoDB table, and then it schedules a pod. The voice training itself took about 4 to 5 minutes, so that would run 100 epochs on the A100, which is the P4. And we came across that as a good balance between the quality we wanted to achieve and the amount of time that we could keep the user busy in the front end. So they were watching that video you watched before, they were joining the lobby and talking to their friends, but we can't leave them waiting for too long while we train. So once that job is done, the room service is notified that that user's training is done, and once all the jobs are done, the game can start.
Matt, it might be a good time to sort of talk about some of the other areas that we sort of added acceleration. Now, fairly complicated concept over here in terms of how we can allocate and deallocate resources. Help us understand how we utilize some of the framework and also for Gen AI in this particular journey.
Yeah, so we built all of the microservices using a framework called Chalice, which sped us up a lot. If people aren't aware of it, it's a Flask-like framework that's developed by AWS, and it lets us write a route and event-driven Python script, and they just automatically convert into API gateways, lambdas, topics, queues, cron jobs, just based on the functionality we want from the code. We were also further accelerated by generating almost all of this code with Claude. So we would write complex specs for what we wanted out of those functions, and then Claude would generate us the scaffolding of the Chalice code. We had to do some light touching up here and there, but it almost all generated by Claude. So let's have a look at our Resource Manager GPU reservation flow. So the Resource Manager is triggered by one of 2 events. One is the audio upload into S3, and the other is a room ready event. So that's when all of the users in the room are ready and the game can start. These jobs will be queued, and they get queued into the same queue in DynamoDB. And that queue is then checked regularly, constantly, for any new jobs that need to be started. If there's no GPUs available, the Resource Manager will estimate the wait time based on the current running jobs and how long they're expected to run, and it will return that estimated time to the front end, which will deliver it in different ways for different tasks. If there is a GPU available, it will lock those GPU resources in DynamoDB, and that's entirely because it was just too difficult to make Kubernetes queries every single time. It was too slow, so we kept track of them separately. And it will then deploy the pod to Kubernetes. It's scheduled, it's running. Once it's all done, Resource Manager cleans that pod up, and we're all good. So once users are in the game, they are publishing their raw audio-video streams to LiveKit, and our inference pods subscribe to those streams in LiveKit. They modify them, and then they publish them back to another set of streams in LiveKit, and then our lobby service handles allocating those modified streams back to random users so that they are puppeting a version of their friend. Players interact for about 10 minutes, they ask the questions, they try and work out who's who through their disguises, and then it's over. Then we're up to cleanup. So Resource Manager gets that cleanup event, job's done, deallocates all the GPUs, releases them in DynamoDB, and then the next jobs can come through. We also had some safeguards in place. We had some cron jobs just to make sure if any of these jobs were overrunning or if they crashed somehow that we would release the GPUs, because they are obviously very expensive and limited, so we wanted to make sure that they were freed up quickly. So altogether, we come back to our final architecture, which is a combination of our microservices bits and pieces, and then our direct A100 access via EKS, and resulting in a seamless, entertaining experience that showcased both Netflix's content and the power of AWS to deliver complex, interactive experiences at scale.
Thank you, Matt. First up, I actually want to acknowledge some of the incredible work the AKQA team have pulled together. Like truly talented technicians, engineers, developers, product owners. It all has to come together, right? The right ingredients at the right time. So, job well done, truly. And I can't believe we accomplished it in 8 weeks. That's incredible. Luke, it's time to now talk about some results and numbers, and nothing speaks greater volume than numbers. Walk us through some of those value that you've had from GenAI to also the GPU numbers.
Sure, thanks Nagib. We're really sort of happy with sort of the outcomes of this project. We had, I think at peak time, we rented about sort of 84 of those P4s. So that was able to support up to 500 concurrent users, which was Netflix's requirements. We also, as we alluded to a little bit before, we probably wouldn't have been able to do this without generative AI building some of the code. So I think, as Matt alluded to, there was, I think, possibly around about 40% of the infrastructure code was generated with Claude 3.5 Sonnet, which was the latest version way back in October. Feels like a long time ago. And 95% of the room service logic code was generated with Claude as well. So that, really gave us a major head start. We wouldn't have got there without some of these tools. And then, of course, like the capacity blocks, that allowed us to sort of allocate and reserve this in advance, which was great. It gave us access to those, hard to get sort of P4s. Actually, I noticed at the keynote this morning, they've announced the P6s, which is the next generation, which has access to the even higher level NVIDIA hardware.
Absolutely.
And we had some really great press attention from this as well, both Mashable and Collider. They did some sort of play testing and they wrote about their experiences, which was really good. And we had the influencers, the YouTube influencers, 100 Thieves. They played through several versions and they live streamed it on Twitch. So I think that got 35,000 views, one of their streams. So yeah, we're just really happy we hit the deadlines and got there on time.
Awesome. Let's summarize a few things. Now, I want to sort of leave you all thinking about one thing, which is think big, start small. It's always important to think big, obviously, on a grand concept, but you do have to break it down into its smallest sort of pieces, bite-sized pieces, so that we can approach it and do experimentation. That's pretty self-explanatory in that case. If we don't experiment, we don't know what to benchmark on, validate what will work and what wouldn't, getting to know and then know. Definitely use generative AI for accelerated development. I think that's a testament to how we've achieved all of this in about 8 weeks' time. And the EKS and ML capacity blocks marriage that we sort of accomplished through Matt's magic, that is a great sort of blueprint on how we can efficiently use infrastructure. And I know the last but not the least, it's, we do this for the customer, to delight the customer. In this case particularly, this was Netflix. So it's important to keep customers in the loop all the way through that journey, not just at the beginning and at the end. You need to get constant feedback in order to modify and change things and pivot as necessary. Some resources over here for everyone to sort of get started on your own journey. I think that you might find it quite useful, obviously, to accelerate some of your decision-making process. And with that, I actually want to ask everyone, please take the time, fill out the survey, and otherwise, we're available. Please reach out to us for any questions that you may have, and also add us on LinkedIn if you want to. But otherwise, thank you so much for your time today.
Thank you so much. I think that was an